It's about that time. Let's go ahead. I am Pat Brown. I'm the moderator for our three-part series. It's a CIM user group technical webcast series, and this one focuses on CIM and network analysis. I'm absolutely delighted to be doing this. I have had a decades-long interest in the Common Information Model, and it's fabulous to see the number of folks that we have signed up for our webcast series. I don't know if you guys can see it or not, but at this moment there are about 170 some folks on this call. It's great. So to just take a quick look at our series, today we have Jay Britton and Alan McMorran doing some discussion about fairly basic parts or basic strategies for using the CIM in power system modeling. Jay will provide an introduction, and then Alan is going to cover the equipment and connectivity and display layout portions of the CIM. Next Tuesday, not Thursday, but Tuesday the 16th, Chuck DeBose will walk us through some of the more complex equipment modeling and some of the more complex models in the CIM, including things like transformers, HVDC, short circuit, dynamics, unbalanced modeling. And then on September 25th, Lars is going to talk about the inputs and outputs to power flow cases. And Jay will come back and talk to us a bit about some current activities that are going on in Working Group 13, specifically projects and outages, which are changes to the model, and also model assembly. Recording of this webcast and all of them in the series will be available at the Technical Webinars Quick Launch link there on the CIM user group website. It takes you to the UCAI YouTube channel, and the webcasts can be accessed and listened to and viewed. One last item before we get started with today's webcast. The CIM user group has its North American meeting coming up this November. It is the 11th to the 14th in Orange County, which is LA, California. And as a participant in this webcast, you are entitled to a 50%, or no, 50%, no, that wouldn't be it, $50 discount off of the early bird registration fee if you register before September 25th. I have to say, if what you hear during our series here is of interest to you, I would encourage you to attend the CIM user group meeting in person. Not only will you get more in-depth CIM training during CIM University on that first day, you can meet the presenters firsthand, and then during the main part of the conference, hear all sorts of good information and success stories about how utilities are using the CIM in real-world projects. So to today's agenda. Some housekeeping items, or one big housekeeping item. With this type of webcast, all the attendee lines are muted, which means you can hear us, but we can't hear you. So to submit questions, please enter them in the question box there on your pull-out window on the right side. We'll monitor that box and address the questions at the end of the presentation, and I'm thinking we will have time for some questions. So here's what we have on tap today. I'm going to give a very brief overview of the Common Information Model in general, and then Jay will talk about what the picture of power flow data is through the eyes of the CIM, and talk about how the CIM is partitioned a bit into subsets or profiles. Then Alan will go on and start exploring the equipment profile, EQ. It contains equipment and the basic equipment and connectivity information that's kind of the core of network modeling in the CIM. He'll also talk about the display layout profile a bit. Each speaker is going to share just a little bit about themselves before his or her segment. So with that, I will introduce myself. I'm Pat Brown. I work for EPRI. I have been here 4 years now. Before that, I spent a career at Kansas City Power and Light supporting control center applications. At EPRI, I work in the IntelliGrid or ICT program, and I focus largely on using the Common Information Model in the transmission domain, so network modeling and also asset health. I'm a member of IEC-TC 57 Working Group 13, as are all of the speakers in our series, and that's the working group that's responsible for the network model related parts of the CIM. Lately, I have been involved with some focused work using the CIM for network model management processes, primarily inside utilities. So just a few sort of high-level observations about the CIM. It is a model for organizing shared data, information that is needed by multiple applications, whether they're inside of one organization or in different organizations. It is an electric utility model, which spans the shared data needed in a wide range of utility applications: asset management, meter, work modeling, network analysis, a wide variety. And it is a model that is growing and being refined over time. We have been working on it a long time and are continuing to do so. There is a group of very dedicated experts who are serious about producing a high-quality model, and there are continuing field deployments of the CIM which identify gaps and shortcomings and really help define solution strategies. So the CIM is divided into 3 sets of standards. 61970, which really is the network model portion, and 61968, which covers meters, assets, work, and other kind of back office sort of activities. And then 62325 addresses markets. So focusing in on the part of the Common Information Model that we care about, the 61970 series of standards, the CIM is expressed in a set of standards. The network model portion of it is the 61970 series. The network model part of the CIM is the oldest and most exercised part of the Common Information Model. There have been more than 15 interoperability tests done on the network model part of the CIM since 2000, and there are multiple small-scale or vendor product-related deployments and one really big deployment of the CIM for network model sharing purposes at ERCOT. It has grown over time. It started as primarily equipment and connectivity in a breaker node form, primarily in the EMS world, but over the last 15 to 20 years, it has grown to include topology, display layout, dynamics, HVDC models are being added, and it is continuing to grow, as you will hear some from Jay near the end of our webcast. And the end of our webcast series, let's put it that way. With that, I would like to pass presenting responsibility to Jay. And Jay, could you just start by telling us a little bit about yourself?
Okay. Am I coming through, Pat?
You are.
All right. I'm Jay Britton. I have been working in the power industry and in network analysis for a long time. I started way back at Commonwealth Edison and then moved to a vendor role, and I worked in the EMS industry for quite a while at Alstom. And for the last year or two, I have been on my own as an independent consultant. For the last 10, 15 years, I've been very active in the CIM development. So with that brief intro, let's launch into the network analysis subject. It's a big subject, and so I'm just in this little session, I'm going to put up just 3 slides, but I'm going to take a little bit of time talking through them and kind of giving an overview of Working Group 13's view of network analysis data requirements. So the first thing I wanted to do is put up this slide that I've been using for the last couple of years. I sat down a while back and tried to look at network modeling mostly from the perspective of an information architecture. What in terms of information management is really important about the network modeling problem? And I came up with these 5 big facts. This is sort of like the magazine headlines that are popular. 7 ways to better hair, or whatever it is. So this is 5 big facts about network modeling. And the first 2 I'm going to talk about sort of together, because the first 2 facts divide the typical power flow data into 2 parts. So if you look at a particular power flow case and you look at it from an information management point of view, what jumps out at me is that about 95% of the data in the case probably is descriptive information about the capability of the equipment that makes up the power system. So for example, a generating unit, you get the mins and maxes of the megawatt, megavar capability, and various other bits of information. With the line, you get the impedance. About everything, you get how it's connected together electrically. And this information is information that is established by the construction process, and it doesn't change. And it's the fact that it doesn't change from one case to the next, or shouldn't change from one case to the next, that's really the thing that distinguishes this set of information from other information that's in that case. It's information that traces its source back to the construction process. Basically, when you complete construction as a part of a normal business process, you would create the base modeling that will be used in studies and should be used in all studies that represent that piece of equipment. And that modeling won't really be changed unless you have some new construction act that goes out and modifies it. Now, in rather stark contrast to that, over on item number 2 here, the steady state hypothesis, that's the part of each case that says what particular situation is being studied in this case. So what components are open or closed in the system, what's in or out of service, what level of load is being studied, what generation pattern, interchange pattern is being studied. All of those kinds of things are part of the particular steady state hypothesis. So you're running a heavy load summer case, so you're running a light load winter case, are you running real-time conditions or nominal conditions? That's part of the steady state hypothesis. That information is the choice of the engineer setting up the case. He very often gets that information from sources, but they're not the same sources that you would get the original data describing the equipment from. And that's what really distinguishes item 1 from item 2. Item 1 has one other aspect, which is that it needs to project forward into the future, which I'll discuss a little bit more when I get to the item on time. So 1 and 2 look at partitioning an individual power flow case into 2 parts. Item 3 is another rather unusual aspect of network modeling information management, and that is that we usually have to do analysis on territory that's owned and or operated by multiple authorities. And so the data comes from different model authorities. In the CIM terms, we call this distributed model authority. And it means that the information management has to be organized so that you can acquire data from other sources and merge it together to form cases. The fourth item is time. Some applications have the luxury of, or business processes have the luxury of focusing on one point in time, but in power system network analysis, we work in many different time frames. We go forward as many as maybe 10 years. In setting up cases, we need to run operating studies, day ahead, week ahead, month ahead, and so on. We do a lot of real-time analysis, and from time to time we also need to go back and look at past events. So we need the ability to set up cases representing anywhere on the timeline, and when we do set up something like a 5-year out in the future case, we run that case, but as time moves on, there may be changes in plans. Generating plant gets rescheduled or something like that, and those impact those future studies, and you need to be able to figure out how to recreate those studies and to recognize when a change in the raw information has impacted those cases. And then finally, item 5 is object identification. And as long as I've been in the business, this has been a bane of network analysis analysts' existence, which is the fact that different parties have different names for the same things. Sometimes it's by choice, and sometimes it's forced because of the application environments and various restrictions on what kinds of names you can create. So this is a set of problems that's it's pretty challenging, and we in the CIM world have been trying to come up with an organization that will deal with all of these requirements. And this slide that I'm bringing up now is a reference diagram that we've been using in Working Group 13 for the past few years. And it shows primarily a single case view, except the actual case is the area on the right inside this light green rectangle. So this is a view of a power flow case, and it's broken into several pieces. The blue outlined pieces are the equipment data. This is the data that is essentially the answer to that first requirement I called out. This is the data that does not change except by new construction activity. And then below that, outlined in red, is an area titled SSH. That's for steady state hypothesis. That's the profile that corresponds to the second major requirement, the steady state hypothesis aspects. And you can see I've listed here some of the kinds of things that are in the steady state hypothesis. And then, of course, there is the solution, which generates a solved topology and state variables. Now, today we're going to focus just on the equipment part, so the blue outline parts. and I think it'll be the third webinar session where we get into the steady state hypothesis parts. But you can see here that what we've done in the overall setup is that a power flow case is divides the data into, I think Pat used the word profile. It's different parts that compose together and form a single uniform model, but they're recognized as separate parts because they come from different sources. And you can see that where they come from in this diagram is laid out on the left-hand side. So the left-hand side has sources of data, and then in the center boxes with the squared corners, these are processes. So there's essentially what you get is on the upper left, you've got this model parts and projects repository that is hypothesized as the source master data for the system as it's built, from which this physical model selection edit process will generate over on the right-hand side the equipment profile that is used in a particular case. Now, mainly what's going on in that particular process box is the selection of the time frame, because the case on the right represents a single point in time. The model parts and projects over on the left are going to have both the as-built and planned construction aspects to them. So the physical model select edit says, okay, give me the relevant information for summer of 2018, and picks out that information and creates the equipment part of the power flow case at the right. Once that equipment is established, you'll see a little blue arrow going back to the left, and that feeds into a set of boxes down there that are in red, that are process boxes, which are the process boxes that set up the steady state hypothesis part of the case. And I show several different process boxes here because those are tend to be different processes for different parts of the steady state hypothesis. In other words, the way that you initialize status might be to go either to the real-time status or a nominal status or a past case. And that's not particularly related to the way that you set up load, which would go to some energy forecasting function and then distribute the energy forecast. Or and that can be quite separate from the way that you would determine a generation pattern. Sort of at the bottom left, I point out that there are a lot of the time SSH is set up from previous cases, so you may be going to saved case parts and using those to retrieve and set up the SSH. Basically, what happens with it though is when you do a power flow, you run setup processes, and I don't here mean to imply that all the setup processes have to be automatic. There can be manual steps, and currently in the industry, there are often lots of manual steps in this process. But one way or the other, you set up the activity or you set up the EQ and the SSH parts of the input to the power flow, and that allows you to generate the output. And the CIM standards are focused on the right-hand side. They're focused on the ability of network analysis applications to exchange the case data that they're based on, including both the input and the output. And it allows state estimators to pass a state estimate on to an analytical function. It allows one power flow from one vendor to pass over to another power flow from another vendor, and so on and so forth. So on this slide, I think I've covered the main items, big facts 1 and 2, and a bit of 4 about time. And I'm going to show one other slide here before we go on to I'm going to say one other thing before I just move off this slide. Where Alan will be focused today is on EQ and diagrams, the DL part. The next session, it'll be done by Chuck DeBosnik on the Tuesday, will go deeper into EQ and a lot of the details of transformer modeling and all, which you know has some complexity to it. And then the final session that Larzola and I are doing will talk about the SSH and also the model assembly process that I'm going to show you in this slide, or introduce to you in this slide. So one of those big facts that you really can't see on that previous slide is the distributed model authority aspect of things. This slide takes up that aspect of the modeling problem, and the picture we have here is over on the left-hand side we have a bunch of I've called them TSOs, transmission system operators. So this is saying I've got an interconnection that's made up of a bunch of transmission system operators, and they're all part of the same interconnection, but they're each the responsible original authority for the data about their own area. What CIM wants to be able to do, or wants to enable, CIM can't force this, but what CIM wants to enable is that these TSOs can get together and decide that they're going to put the models of their system, structure the models of their system such that they form this green thing in the middle called a unified grid model. So this just means that what TSO A supplies as the model of its territory will fit together with its neighbors B, E, and F, because in their agreement about the unified grid model to come together on that, they will have agreed on how the boundaries of their models fit together. And CIM has a formal mechanism for defining those boundaries and making that boundary agreement. So once you get to this unified grid model, then what can you do with it? Well, the objective is to be able to support from the unified grid model all the kinds of studies that need to be created in this interconnection. We all know that there are a variety of different kinds of studies and scopes of studies. Not all studies will look at the same territory. Some studies may be focused rather locally on a part. Some have a wider view. In some interconnections, you might occasionally run views that cover the whole territory. Virtually nobody runs studies that cover the entire territory, both in terms of breadth and voltage levels. So if you get into a true, totally unified grid model, going all through all voltage levels across all spaces, you would never get a study that actually ran everything. But what CIM tries to enable is the ability to easily extract the pieces that make up the scope of a particular study type over on the right-hand side, and provide the mechanisms for doing those case assemblies in each case from the same set of core master data. And I can just say, I'll close here. We'll just mention Big Fact 5 was naming. It doesn't show up very directly here, but this picture is the best place to see where it comes into play. Typically, when you import into study environments, you sometimes run into specific naming restrictions, and you need ways of translating. What we're basically doing is putting one unified identification system in place in this unified grid model, and then a translation system so that you can generate alternative namings in a particular environment where you need it. And with that, I think I'm going to turn this over to Alan, and he will give you a little bit more detail about the equipment part of the modeling. And Alan, can you just take control, or do I have to do something?
I have no idea. Let me see. Yeah.
I just transferred control to Alan, so we are seeing your screen.
Okay.
And Alan, if you could start just by telling us a little bit about yourself, that would be great.
Sure. Well, I'm Alan McMorran. I work for a company called Open Grid Systems. We're based in the UK, here in Glasgow. And I'm, as Pat has already said, I'm a member of Working Group 13. I'm also on, I think, 14, 16 and 19, covering distribution markets and the coordination between all the other groups. I was previously at the University of Strathclyde, where I did my undergraduate, did a PhD, and then was a postdoctoral research fellow for many years. Open Grid Systems has been in existence for 4.5 years now. We work with utilities, vendors, consultants all over the world, and we do lots of work around about open standards, around about data integration, data modeling, and mobile applications as well for utilities. I also wrote the first edition of the EPRI CIM primer, and I've written lots of different papers on the CIM, on software for power engineering, and so forth. So, as Jay's already said, today I'm going to talk a bit more about the CIM network model, focusing on things like the equipment, and then we'll move on to the diagram layout. So before I kind of really delve into the different profiles, it's worth understanding just what CIM is, how it's put together, and what we mean when we talk about the information model and so forth. So there's always lots of numbers when you deal with the IEC standards, the same with any other organisation really. And 61970-301 is the UML model, and it defines the components in the power system. It was originally used by the EMS. That's now obviously extended out into covering all aspects of the power industry, including distribution. So the scope of the CIM really has expanded from its kind of roots as an EMS API, which is the Energy Management System Application Programming Interface, is the true name of Working Group 13, as that's where it originated, but of course it's now expanded out far beyond that. When it comes to the way we describe the CIM, we use UML, and which is a way of defining, is unified modeling language, a way of defining data models. And the majority of CIM classes have something called identified object as the root. And to try and explain how the inheritance works, I'll use an example of a CIM class. So a breaker, if anybody is a power engineer, they should know obviously what a breaker is. It's a mechanical switching device capable of making, carrying, and breaking currents under normal circuit conditions. And this is a very common component within any electrical model, and obviously something that's within the CIM. So that definition there is the textual definition of this element from the CIM UML. But the CIM uses an inheritance structure. So the way that is we're saying that we have a breaker, and the breaker has an in-transit time, but the breaker itself is a type of protected switch. because there's many different types of protected switches. These are basically switching devices that can work and do protection, as the name would imply. And so they share common attributes for things like current ratings. And then the switch itself is a generic class for any piece of conducting equipment that operates as a switch in the network. And so you have things like this normal open condition, whether it's retained, which means that if we are running topology analysis, is this something that should be collapsed into the topology when we're doing an equivalent network, or is it something that should exist as essentially a zero impedance branch? And so when you're looking at this model, you can see that a breaker is a type of protected switch, and it is a type of switch. And within the CIM UML, we have lots of different types of switches and different types of protected switches, but they can all be treated as a simple open and closed switch should you need to. But once we start moving up the inheritance structure even more, we say that as a switch itself is a type of conducting equipment. And this is an abstract class. This is just something that refers to any piece of equipment that conducts electricity and contains attributes, when it's got terminals attached as attributes to denote the phases. Equipment that sits above this is just any resource on the power system that's a physical device and could be electrical or mechanical. So it may be conducting electricity, it may not. We then have a power system resource, which is a very generic abstract class to cover any sort of resource within this power system model. And then we have our identified object at the top, which is our abstract class, saying that this is something that has an identity and a name. So looking at the breaker here, it means the breaker has all of the attributes of everything that's its parents. And you can see that the CIM starts with quite a deep inheritance structure to it. And there's very good reason for doing that, and it can be very useful, especially from a kind of software development perspective. So we also obviously define connectivity within the CIM. We use connectivity nodes and terminals to define the interconnections between components. So these can be components like breakers, loads, lines, transformers, shunt devices, and they don't associate directly with each other. Instead, any piece of equipment has one or more terminals, and then the connectivity node represents the zero impedance point of connection between the terminals. So if we look at the UML for that, it's saying that we have here conducting equipment, which has zero or more terminals within the model. In reality, when we use this, we want a conducting equipment to have at least one terminal, maybe two terminals. In some conditions, it may have 3 or 4 if we're doing 3 or 4 winding transformers. And the terminal itself points to a connectivity node, but the connectivity node may have many terminals associated with it. So that's what the UML looks like. But as with a lot of this, it's sometimes much easier to try and understand these concepts if we look at a kind of instance, a diagram. So if we consider a simple single line diagram, we have here 3 components. We have a breaker, a load, and a line segment. And each of the components has one terminal, and they all associate with a single connectivity node. So here we have 3 terminals, we have 3 pieces of equipment, and we have a single node. So from this, we can navigate from the breaker through its terminal to the node, and then find the other components that are connected there. If we extend the model slightly, obviously the breaker is going to have 2 terminals. So here we have 2 terminals associated with the breaker with a node on either side. This means if we're doing measurements in the breaker, for example, the measurement can be tied to the breaker and tied to the specific terminal either side. So if you had something measuring voltage, for example, you would be able to say which terminal it was on, because if the breaker was open, the reading could obviously differ from side to side. So if we expand out our inheritance tree a bit, we have here the original hierarchy on the left-hand side that we showed for our breaker with its protected switch, conducting equipment, power system resource, and identified object. We've also added in the terminal and connectivity node, so we can see how our conducting equipment here can have multiple terminals, and the terminal goes to a connectivity node. Then below conducting equipment, we start to see some of the different classes. There's more than just these that actually represent any pieces of equipment that can conduct electricity. So an energy consumer is a piece of conducting equipment, and it will likely have one terminal representing a load. We have power transformers, and we have AC line segments. And we can see here that on our protected switch, we've actually got 2 subclasses. We've got our breaker and we've got our load break switch. So you can see that if you're considering how you're actually going to deal with this data, if you're wanting to write a very simple topology processor, you can simply treat everything as conducting equipment, navigating from terminal to node to terminal to equipment and so forth until you've propagated throughout the network. And then we can start saying, well, we want to deal with switch conditions. We can treat it as a switch. In programming terms, it's known as polymorphism. Showing a bit, in fact, I did some computer science as well. But it means that you can deal with things at the abstract level or the detailed level, and it means that we're not duplicating things. It's a very much as an object-oriented way of defining the components within the power system. So to try and understand a wee bit about how this actually maps across to real data, we're going to look at how we would model a substation, translating the schematic into CIM components. So this is what we have on the screen is a simple single line diagram for a substation, something you've perhaps seen in EMS. And these electrical components can be mapped to components from the IEC 619700301 from the CIM UML. So a lot of the main components map directly to one piece of conducting equipment, where we have the energy consumer mapping to the load, AC line segments to the line, or breakers, or busbar sections. The generator actually maps to two components because we are mapping the synchronous machine and the generating unit itself. The reason for that is that a single generating unit may have multiple synchronous machines. For the purposes of simplicity, we'll keep it as a one-to-one here. And the synchronous machine is there for converting mechanical power into our alternating current. So here we've already started to pull in some of our CIM classes for our components. The transformer is one of the more complex parts. Anybody that's done anything with power system data probably knows that transformers are generally the 10% that takes up 90% of the time in any kind of data translation, because they are very complicated pieces of equipment, and there's very many different ways of modeling transformers across different applications. The way the CIM does it is that we have a single power transformer container class. In the example we have here, it's a two-winding transformer, so we create two power transformer end objects that go within the power transformer. And we can have in this case, you can have tap changers. So it could be a phase tap changer, a ratio tap changer, and it's associated with the power transformer end representing the winding that the tap changer is against. So the class structure for transformers here, if you're looking at it in the right-hand side, we have our power transformer, which is a type of conducting equipment, so it has its terminals and can be treated from the purposes of things like topology analysis as any other piece of conducting equipment with more than one terminal. There was a big change to the CIM transformer model a few years ago because there was a desire to have a harmonized model for transformers that would work all the way from high voltage transmission down to unbalanced low voltage distribution. Especially in North American networks, there's a lot more unbalanced modeling goes on, and the modeling of things like transformer tanks. So here we have what we can do is the power transformer can contain multiple transformer tanks, quite often representing a single phase, and then there'll be transformer tank ends, which are going to have parallel to the power transformer end that we see in transmission. So the example we are doing, we're assuming it's a balanced three-phase transmission model. So we would have a power transformer, which would have two power transformer ends. The transformer end class here is the abstract superclass of both transformer tank end for the unbalanced distribution and our power transformer end. The commonality here is that you want to define things like different ways of doing impedance with star or mesh, and doing things like the core admittance. The tap changers also fit in at the transformer end part of the model. So our tap changer class here, which is an abstract class saying this is a tap changer. Then we have different types of that. We can have a simple ratio tap changer, which will allow you to change obviously the ratio of the voltage. And then we have phase tap changers. And phase tap changers, there's many different types of that when we get into symmetrical and asymmetrical phase tap changers or a simple linear tap changer. There's also a couple of subclasses for defining both phase and tap as tabulars, where you're defining essentially a table of steps and corresponding changes to angle or voltage. So a transformer end, whether it's the power transformer end or the transformer tank end, can have a phase tap changer or a ratio tap changer, and we can put it on either side depending upon how it actually is modelled out in the field. We're not restricting the tap changing to one side of the transformer. So in the example shown, each of the transformers now actually results in mapping in 6 CIM objects, at least. We have the power transformer, and it contains 2 power transformer ends. Against a power transformer ends, we will have a ratio tap changer on one side, and we will have a transformer mesh impedance, if we're going to define the impedance between the 2 sides and using a mesh form. There's actually a couple of different ways of defining the impedance, because in some systems we will define the impedance values explicitly, in others we will have a separate class so they can be shared across instances. A lot of this gets into, again, the transmission versus distribution, where at transmission it's very common to just explicitly state values in every piece of equipment, whereas at distribution it's a lot more common to have catalogues of values that are shared across different instances, allowing one change that impacts across all of the transformers of a different type to be made at one point in the system. Obviously, if the transformer has a tertiary or quaternary winding, this can be represented by adding in another instance of the power transformer end or another 2 instances of the power transformer end. You can also see here that the power transformer itself has 2 terminals, and each of the ends then also has an association with the terminal, so that you can tell which side the transformer end is actually connecting to. The current transformer we had doesn't actually map at the moment directly into a piece of conducting equipment. This is because in general the CTs are passive pieces of equipment. They're not actually doing anything active that's impacting upon the network conditions. So the current transformer is represented as having a measurement assigned to a terminal on the system. We also have, obviously, containment of the data. CIM has a generic abstract class called equipment container, provides a means of grouping together pieces of equipment that represent both electrical and non-electrical containment. There's then specific subclasses of equipment container, so voltage level, bay, substation, line. They can all contain equipment, and quite often when we're getting into doing things like the profiles, which Jay has mentioned, we can place additional restrictions upon this. It can be at a transmission level. You may wish to restrict what goes into a line to only being line segments. Whereas when we're using the line container at something like distribution, there may be a need to put things like some switchgear or transformers into the line container itself. So part of the reason there's flexibility is that the data can be contained slightly differently depending upon the country, depending upon the level of the network that you're modelling at, but the restrictions are placed at the profile level, so that you can still validate your data. So within substations, there's a containment hierarchy, so that you have a substation can contain voltage levels, or it may contain bays. Not every system and not every country actually uses the bay concept, so it is an optional one, but the flexibility is here to allow you to ensure that you are retaining the modelling of the data as you currently do internally. So you would say that you're modelling your substation. It's fairly typical to look at a substation and see the voltage levels that are within that, representing the kind of islands of voltage, with obviously transformers sitting between them, with the transformer itself sitting inside the substation. The substations and the line container themselves are contained by a subgeographical region, and then subgeographical regions are within a geographical region. So this gives a way of providing essentially what is a navigation hierarchy for the data. There's different hierarchies for viewing the data, because there's also control areas which may or may not correspond to the subgeographical region containment. So quite often we get into the questions of, what is the hierarchy within the CIM, and quite often what that's really meaning is what's the hierarchy for a view, and it depends upon the application. If you're coming at this data from just wanting to navigate down through it to find the different parts of your network and see what's there and what your internal organizational hierarchy is, it's quite often geographical based. But that can differ for a control area hierarchy or a load hierarchy. So this is just an example of the kind of nominal geographical based containment that we have within the CIM. So if we look at the schematic that we had before, what we have here up in the top left, we have one of the voltage levels. So this is a voltage level that contains an energy consumer. It contains a breaker. It contains the terminals either side of the breaker, one on the consumer, and then the nodes to define the connectivity between the energy consumer and the breaker itself. These are within a voltage level container, and the voltage level has a base voltage association to the 33 kV, which represents the nominal voltage of that part of the network. The other side has a similar structure where we have our breaker, we've got a couple of nodes, and this time it's a 132 kV voltage level. We now also then, the node at the top of that particular voltage level then connects via a terminal to the AC line segment. Our AC line segment itself has a direct association to the same base voltage of 132, and it is within a line container. The larger voltage level to the bottom has our busbar section, it has a breaker, synchronous machine and generating unit, and also has the measurement that we mentioned that represents the CT that goes against the terminal. The busbar section is the one that quite often seems counterintuitive the first time you see it. The reason that because when you consider a busbar, lots of people will think, well, a busbar has multiple pieces of equipment attached to it, so there should be multiple terminals on the busbar. But in fact, the way it is modelled is that there is a single connectivity node. The busbar section has a terminal, and that goes against this connectivity node. And everything going into the busbar section has a terminal connecting to the node. The reason for this is that it means that there is one way of defining the connectivity on the terminal connectivity node association. Otherwise, what would happen is the busbar section itself would essentially be behaving as a node, and so you have a special case. This way, we have only one way of defining the connectivity using the connectivity node, and it makes it a slightly cleaner model. And it means, but we're still modeling the equipment that's there, because obviously we have things like measurements that are tied to the physical piece of equipment that is the busbar section. So it has to be modeled when we're doing this connectivity-based operational style model. When we now add in the transformers, we look at on the left-hand side, we have a 33 kV to 17 kV power transformer. And we have on the right-hand side, we'll have our 132 to 17 kV transformer. So when we drop the objects in, we have here it's the same instance examples that I had earlier on. The power transformer ends associate to the same base voltage definitions. And these base voltage definitions are shared throughout the model. So looking at a typical transmission system, for example, you're maybe only going to have 5 or 6 base voltage instances because they're not representing the measured voltage at a point in time, because obviously that's going to vary up and down across the network. They're representing the nominal voltage. And so you can use them for doing things like per unit voltage calculation and so forth. Around about our voltage levels that we have there, they are contained within a substation, and the transformers themselves, because obviously they span between voltage levels. So we can't be placing the power transformer in one voltage level or another. So the transformers exist within the substation, but they're terminals and connected nodes that are in voltage levels on either side. So if we take our model we had there, we can see how it corresponds to the model that we had before. So we have our schematic on the left and the resulting CIM object model on the right. So that's what we saw there was really a connectivity-based model. So it's a node breaker model, but we also have support for topological bus branch modeling within the CIM. So in the CIM, we refer to topological, we mean bus branch, and connectivity means node breaker. So in planning applications, it's a lot more common to use a bus branch model because that represents buses that are computed by a topological processor. And the CIM supports both views of the data, and they can be exchanged together. So in a bus branch view of the network, there's a number of buses and a number of interconnecting branches. Quite often in the CIM, there'll be AC line segments or there'll be transformers. So looking at this, we can see that we have our buses here. And an operational view of that same data, though, may be slightly different. Because in the operational view, what we can see is we're essentially adding in switches. And the switch configuration may alter how the buses are computed. So in our example we have on here, we have a couple of closed switches between in the top left and bottom right, resulting in single buses. And we have we have a couple of open switches in the top right and bottom left, so which is obviously creating a split between the busbar sections along the bottom. So different switch configurations will result in different bus configurations. If we close a switch, it combines together one of the two buses at the top to form a single bus. Similarly, if we open some switches, then we're creating buses where they didn't exist before. So depending upon the purpose of the exchange, a utility may be required only to export these computed topological nodes rather than a detailed network model. And this may be dependent upon whether you're wanting to exchange only a simplified model with a neighbor, or whether you're wanting to take a model and use it with something like a powerful application, which is probably more just looking for a bus branch model. So the topological node connectivity is actually defined in the same way as the connectivity nodes. So a terminal can have one or more topological node associations. And this is the equipment essentially on the edge of the topological node. So if you're wanting to, a topological node, when you look at it, will have things like terminals that point to line segments, that point to energy consumers, synchronous machines, shunts. There will be terminals internally that have no topological node because they've essentially been collapsed down. Things like closed switches that are not retained will be collapsed down into the topological node. So a terminal can point to a connectivity node and a topological node. And when dealing with the data, you can know whether you want to be dealing with the topological view or the connectivity view, and they don't interfere with each other. Obviously, changes to the connectivity model should result in you recomputing the topology, but you can exchange the two of them simultaneously and allow the receiver to choose which model it is that they want to look at. So it's a quick summary of what we looked over there. The CIM equipment profile defines the components in the network model and the connectivity, and this is really the core electrical model, and this is where a lot of the CIM is built from. Everything else essentially starts at the core electrical model and builds out from that. And it represents the state of the network at a single point in time. While there is things like schedules in it, these are representing normal load schedules for a particular day or month. We're not trying to model how a switch will change state. We're treating this as a single state of the model. If you want to model how things will change, we start getting into incremental models and so forth, but we don't want to overcomplicate this too much. So the static model, the steady state hypothesis, and the measurement data, these can be used to provide different hypotheses or different starting states for the same underlying state model. And the connectivity and topological nodes behave in a similar way, but as I say, they represent different levels of detail for the network, and there's valid reasons for both of them being used for different purposes. And the idea behind a lot of what we're doing here is to try and make sure that both can be supported, both can be exchanged, and you're not having to either simplify a detailed model or represent a simplified model in a detailed way in order to use the CIM. We want to try and make sure that we support both of them and support them both simultaneously. So I think that's then the first part there, talking about the equipment one. Will I just go straight into the diagram layout, Pat, or?
I tell you what, while you are on that presentation, why don't we take some of the questions that have come up that are specific to the equipment profile. So here you go. The measurements, voltage, current, etc., can they be represented by the CIM? Are they associated to terminals or connectivity nodes?
There is the measurement. I mean, I'll let Jay nip in here as well, but there is a measurement class, and there's subclasses for describing things like analog measurements, discrete measurements, and the measurement goes against a piece of equipment and a terminal. We don't generally tie things like measurements to connectivity nodes because connectivity nodes are really a kind of artificial construct. They're used, whereas things like terminals and equipment do represent something that is out there on the system, and measurements will be tied to them. So the measurement points can be represented, and you can have measurement values against the measurement points as well. Quite often when we see operational models exchanged, the measurement, whether it be analog or discrete, has a SCADA reference against it. And so when you're using this data, the idea is that you can actually obtain the real-time data from the SCADA using the SCADA measurement point reference to fetch that from an external system. You want to add anything, Jay?
No, that's good, Alan.
All right, next question. How to model step size and from to bus regulation for a transformer in CIM?
The model I showed for the transformer is simpler than everything that can go with that. There is regulating control that can go against a tap changer. So when looking at a tap changer, whether basically there's different types of tap changer and different ways of representing what the steps are. If you're looking at something like a simple ratio tap changer, it will have a step voltage increment defining what the I think it's in percent what that changes for each of the steps, and then you have a maximum, minimum, normal, neutral step setting. And then you can have on the a regulating control for the tap changer and go against it, where you're setting things like the target value, dead bands, and so forth. So that allows you to define the kind of details of the tap changer and then the regulation information that goes along with it.
Yeah, the transformer models have undergone a number of different evolutions and gotten more sophisticated, and they cover quite a few different circumstances. And I think Chuck will cover that next week, won't he, Pat?
Yes, I was just going to say that. Yep.
Yeah.
So the step in Chuck's toes. Okay.
Oh,
No, you've prepped for
yes,
that's
correct.
right. It's just an hors d'oeuvre. You did great. Okay, next item or next question. Is there a generic non-hierarchical container like tag in the CIM?
No, but it's something. Well, the simple answer is no, but it is something that we have discussed a number of times because it has come up. What we want to do is make sure that something like that doesn't end up being used for some of the existing hierarchies that are there and more fixed. So, but it's something that has come up in discussions. I wanted to get in there before Jay, because I know Jay agrees, and Jay would probably say we should add it tomorrow. But I think it's something that has been in discussion within the working groups, and it's really a case of us coming up with a solution that works well and works for a number of the different applications. And we also need to make sure we understand what the applications are that need this, rather than just being something that's ad hoc. Because when you add in things that can be used for when you add in a field within something that's unclear, it gets used for 10 different purposes by 10 different people, which means it's hard for somebody else to interpret what it's for. And therefore, when you're looking at defining an exchange standard for data, you question, is it valuable if you're defining something that nobody else can interpret?
Yeah, one sort of caution on looking at the CIM is you need to understand that the aim of CIM is to define common semantics for exchanged information. It isn't to define all of the information that's required by a particular product. So there are some things that, for example, are necessary within an EMS that haven't come up in the constant context of an exchange, and won't therefore have made it into the CIM modeling yet. And this is an ongoing evolutionary process. As we get new problems that come in, we annually add to the CIM to cover those exchanges.
Okay, next question. Is the voltage level of a conducting equipment stored as an attribute of the equipment or derived from the voltage container that it is in?
It's a combination of things. There's two ways it's done. If you're looking at data within a substation, it will be within a voltage level, and the voltage level is a base voltage. So you will derive the base voltage of a piece of conducting equipment in that situation by looking at the voltage level it's within, and then that's base voltage. If we have a bay situation, you would look at the base voltage level, and then it's base voltage. For equipment that is outside the substation, so for transmission, that is generally the AC line segments. We move into distribution, then we're perhaps looking at more pieces of equipment that are within the line container, because it could be switches, line segments, it can be things that are on the line, even loads that are not considered to be part of a substation. In that situation, they have a reference to the base voltage. So it's not an attribute per se, it's a reference to the base voltage. So as I said, you may have 5 or 6 base voltages instances in your model, and then you can look, if you look at them the other way around, no, we can look at a base voltage and see there's maybe 10,000 objects associated with that base voltage. So it does mean if you want to change the base voltage of something, or if you've perhaps mistyped it or somebody wants to update it, you're looking at it at that kind of level. So it's not an attribute per se, as it's a reference to the base voltage object, but in reality it works the same kind of way.
Excellent. All right, here's a tougher one. A container for what kind of equipment is the class plant designated? Why being asked, is a hydropower plant a plant? The CIM would say no. And I think, is this perhaps a question on inheritance between plant and hydropower plant? Or?
I think I think the plant class is a type of equipment container, if I remember correctly. And I think the intention for that is that if you're doing detailed modeling of essentially a generator, um, while the generator itself will have a substation, if you're wanting to model more of the equipment that's within a generating station, it doesn't really make sense to try and cram everything into the substation container. So the plant container is there to provide a way of defining the containment that is different, that's slightly different to the substation. In reality, we actually don't see it being used much at all. I think it's because perhaps when we're looking at models, it's the generator itself is being represented by a generating unit and synchronous machine, and that's the level of detail that's required, and putting them in the substation is actually fine. So the plant class is something that I don't think it's in any of the NSOE exchanges, and we've certainly not seen it in exchanges we see coming from clients.
Yeah, there's a lot of products that are still in the mode where everything is in a substation except lines, which is kind of why the substations are the container that we see used most. And plants were defined actually as our lines, as being able to contain any kind of equipment in CIM, but it doesn't typically get used that way very much yet. But we see this as something that's going to change over time. And I would expect that one of the uses of the plant container ultimately is to contain things like wind farms. And
yeah, I think it's that, and I think it's also because the generators at the moment are generally modelled more how the transmission operator sees them rather than how the generators themselves perhaps model their internals. And I think as we move more towards seeing detailed models of the actual generating stations themselves, we'll see it being used more.
All right. Questions are coming in very quickly, so I'm trying to sort them out and figure out the ones that are most applicable to the equipment and connectivities discussion we have just had.
Yeah.
Here's one for you, Jay. How does CIM handle equivalence modeling?
This is I just barely sort of introduced the idea on my last slide of studies assembled from model parts that make up a unified grid model. And this is a little bit of an area that's under development and has been discussed a lot in recent meetings, and it looks like we're shaping up a direction. And the direction that we're going in is that within the framework of that unified grid model, you could have any number of different model part instances representing a given territory. So, you know, let's say one part of that grid model was the territory of a particular utility. And in that utility, in studies run by that utility, they want the detailed view of that utility. But when somebody else runs a study, one of their neighbors, they need a model of that utility, but they'd like it in a reduced form. What you can do is run a network analysis routine against another solved power flow to generate a traditional mesh equivalent of that area. And as long as you maintain the same boundary connections, you can use that equivalent version within an assembly in the same way that you could use the original detail. You could also do other kinds of simplifications where maybe you're not running mesh equivalents, but you're just throwing away parts. And in the third session of this webinar, I will get into that issue a little bit, but I don't think anything in this webinar series is really going to take on that subject in detail. In some of the other writings that Pat and I have been working on, we've been working on that aspect of the problem because it keeps coming up, and it is important. It's important to the flexibility, being basically important to the idea of being able to use master sources to generate all possible kinds of studies that are done in the utilities.
Very good. Okay. And this is a question does the CIM support fault level and dynamic data exchange? I can answer the second half of that question. If in the world of dynamics there is a CIM model articulated for between 200 and 300 standard dynamic behavior models for generators and loads. And Chuck will go into some detail on that in next Tuesday's session. Jay or Alan, do you want to add to the fault level part of that question? The entire question being, does CIM support fault level and dynamic data exchange?
Alan, did you have an answer?
No.
Okay.
It's not really. To be honest, it's not really something we deal too much with. We're more at the network modeling side, so I was going to open you with.
Yeah, I think the fault modeling is supported, and if the results are expressed the same way a power flow is expressed, fault output would be supported. But to be honest, this is not an area that's really been tested very, very well from the point of view of people actually trying it out and setting up use cases and so on. So I think the short answer would be it's our intent to support it, but I wouldn't guarantee right now that it's ready.
Okay, another question. How does the CIM model a DMS feeder and the association for a feeder and its feeder breaker? Alan.
Yeah. Right now, my answer would be not very well. That's because I would like to see some changes, but I won't get into internal IC politics. Really, at the moment, the intent is if you want to find a piece of equipment, if it's a feeder will be modelled as a line container at the moment. If you want to find the breaker in the substation that is for you, and you will do topology analysis to work out where the connection goes into. I personally would be quite happy to see the feeder modelled as a separate container. I think there's some value in that, but that's been some internal discussions within the IEC for a couple of years now, I think. And part of it gets down to there is big differences in different parts of the world and different utilities as to how they model their feeder and what is meant by the term feeder. and how you model essentially when does something stop just being a secondary line between primary and secondary, and when does it start becoming feeder, etc. So at the moment, the only real way to do the feeder and find its breaker is to follow through the topology of the network to define the switch essentially within the substation that represents the point where the feeder comes off from.
So there's a kind of a follow-on question to that. Can you comment on the state of the CIM model for DMS? Is it ready to be utilized?
Well, I want to add one thing to Alan's comment. There is the possibility of using the model part and model part boundaries to divide feeders from the substations. But
yes, yes. When you're right. Sorry, Jay. The example you were showing of doing the model as the kind of Russian doll nested kind of parts within parts and with nodes between them is you're quite correct. It's another way to do it, whereby there would be a node that represents the point of where it stops, where the kind of like the secondary medium voltage model almost connects into the feeder. But if you're looking at it purely from the CIM model point of view, if you're looking just pure CIM data, then at the moment it's a case of you can define the connectivity model for it, and you can define it as being within a container for each feeder, but there's no feeder class that you're looking at it as being a line. And then you have to know that is representing the feeder. If your purpose is to do topology analysis, state estimation, if you want to run power flow, then the model can do that, and the model has the support for defining unbalanced models, for defining all the connectivity right the way down to low voltage. And I mean, we are using this with clients to define low voltage distribution models. Both for DMS, for mobile applications in the field, for doing network modeling for analysis, and it supports that. But if it's where it perhaps needs a bit more enhancement is around about the kind of navigation containment, because that is just generally very useful for people in being able to follow through the model.
Yeah, I agree with that. But I would, just to sum up the answer on the DMS side, I would say that CIM absolutely can be used in the DMS, and an awful lot of work has gone into the CIM over the last few years to do unbalanced modeling and to represent the kinds of transformers that are in the distribution networks, and it's really the right place to go for DMS. But that's not to say it's complete.
No, and I think a number of
Alan's point about line feeder container, that definitely needs to be addressed, and it's on the agenda.
And I think I know a number of vendors do already support CIM for DMS import and export, so it can be used by them for defining the models.
Excellent. We have absolutely an overwhelming number of questions coming in, and they are really good.
Are we gonna have? Does Alan still need to do display layout?
I tell you what. Why don't we go ahead and have Alan do the display layout part, and we will come back and answer questions.
Yeah. Sure. It's actually diagram layout.
Yeah.
We should.
Oh yes.
That's true.
I always get it wrong too.
As long as you don't say graphics exchange, it's fine. Okay, I'll do the diagram layout part. As we've already discussed, the CIM is widely used for exchanging electrical network data for transmission, planning, and distribution. And often, though, to aid understanding of electrical models, you want a single line diagram, and people want geographical overviews as well. And the CIM does make a distinction between geographical data and diagram layout information. And this is something we've had discussions with the IEC, within interop groups, and we've had obviously with customers and clients, is that there is a distinction between something's physical geographical location and perhaps a diagram that is derived from that, or is a pseudo-geographical. So we have to make sure, and storing them differently is very important, especially as more and more analysis, data analytics is done on very detailed geographical views of things. We have to make sure that we're not, for example, disturbing geographical equipment positions in order to make a diagram look pretty. So a great deal of effort and cost is often goes into build and maintain diagrams. There is obviously auto layout programs from many different people, but I think anybody that's used those knows that quite often you will do that, and then you'll spend some time moving things about and making it work the way you want to do it. And that's something that needs to be exchanged and saved, because there is effort and cost that goes into doing that. So the CIM diagram layout profile enables users to define these diagrams in a CIM format with direct links into the underlying CIM network data. So part of this is going to be synchronized exchanges, because a number of systems exchange the electrical network, the domain data. And many of these systems have graphical interfaces. And users perhaps want to see the same single line diagram layout from one system to the next. Or it could be that you're wanting to exchange a diagram with another utility, or you want to exchange it between a distribution system operator and a transmission system operator. And there's a lot of power and a lot of benefit in making sure that make sure somebody has the same diagram you do, and that it's kept in sync with the network model. So the key question is is it better to exchange the diagram as a graphic or a layout? And by graphic, I mean if somebody gives you a SVG, scalable vector graphic file, or somebody gives you a PDF or a PNG or a JPEG, that's them giving you a graphic. It's giving you something that's pre-rendered. Or do you give them layout data? Because the former is a graphical rendering, so it comes with all of the information about icons, styles, colors, something that you can look at and view. Whereas the latter is really providing coordinates for each component, and optionally you can give them those style references. And then the receiving system uses the domain data, so it uses our electrical network model, it combines its layout data, and then it generates the diagram. And the latter is the approach that we took with the CIM when we were doing this, because from speaking within the IEC, within the working groups, from speaking to utilities and from speaking to people about their use cases, what we found was that users wanted to view a network model, and if they were doing it in their system, they wanted to make sure they were seeing it with their own icons, with their own colouring, with their own system, because it was something that was more instantly familiar to them. So they didn't particularly care what somebody else's icon was, they really didn't care what somebody else's colour was. But what you want to do is make sure that the diagram will look the same in terms of its layout. So the diagram layout profile builds on the existing CIM model, and we added in classes for describing this diagram layout. And it means that we can reuse existing technologies like the RDF XML or XML schema, and also means that you can exchange the diagrams, including any updates, along with the network data. So when you do exchange of network data, you include the diagram data along with that, and it means everybody's kept in sync. You're doing it the same serialization format, you've got the direct links, and within your own host system, you can make sure that you're keeping everything aligned, and you're not trying to line up a diagram with changed network model later on. So the diagram layout profile just becomes another profile linked into the network profiles. So for instance data, we've got our equipment profile, which we can spoke about before. We've got state variables, we've got topology, we could have measurements, we could have the steady state hypothesis, and we've our diagram layout profile, which becomes another one within the group. So it means that you can use the diagram layout profile on a number of existing exchanges. So any existing network data for planning or operations can now include a single line diagram. And the profile that we defined was used by ENSOE for transmission. We will use it distribution for distribution models, and it's the same profile. It's unchanged. We're just using it with different network models. And so we can use it to include internal substation schematics. We could do network overviews. We could do pseudo-geographical data. There's even been talk of us doing the CIM for dynamics, where we could do dynamic block models for the user-defined models and exchange them with a diagram using the CIM diagram layout to describe that. So this fits in with what we're trying to do within the IEC and what we're trying to do with the CIM to create modular profiles. So you could create a planning profile by taking equipment, topology, and state profiles and putting them together into planning. You could create your operational one by taking your equipment and measurement data and sharing the equipment profile between the two. And we could do one for distribution, where we could take our equipment, we could take the measurement, we could add in geographical information, because distribution systems generally have a lot more use of geographical information than we find at transmission. And then we could say, well, we want to add diagrams to both operational and distribution, and we can reuse that same profile in both of them. We don't need to define a different diagram profile for transmission as for distribution or for planning or for node breaker. We're reusing it. So for the UML we defined for the diagram layout, it's actually not overly complicated. It's a few classes, and this is it in its entirety on the screen just now. But I'll go through the different parts of it to make it maybe a wee bit clearer. So at the basic point of it is you have a diagram object, and this kind of one or more diagram object points. So if you consider some pieces of equipment may just be modelled as a single point on the network, or you might define a line running between substations with multiple bend points on it. So it's going to have multiple diagram object points. They have a sequence number against them. We have an X, Y, and Z position. The Z position may seem odd, but we're actually using that because we're doing some stuff with elevation data for geographical derived diagrams, where you want to be able to see how something looks in a three dimensions rather than just on a flat map. So we wanted to make sure we had that. The diagram object itself has got things like an offset, so we're defining icons and a point. How does it offset? What's the rotation on it? So if we say it's a load, it may have a kind of triangular icon, and we can say whether it's at 90 degrees, minus 90, 180, so forth. We can also say it's something a polygon, so if we've got multiple points, should it join up at the end? Is it representing an area rather than a line? And then anything that is our identified object, which I'd mentioned before in the previous presentation. So at our very top level of our class hierarchy with identified object. So identified object can have multiple diagram objects associated with it. And that's because the same piece of equipment, the same substation, the same line may appear in multiple diagrams. Because of course they will. If you're wanting to do an overall overview diagram and you're wanting to do an internal substation, you're going to have the substation in it, but at different points on a diagram, depending upon the context. So our domain data is anything that inherits from identified object, and this can be the electrical components, it could be containment components, it can be measurements, so you can plot on a diagram the information about the measurement, and you can put dynamic block modeling. So anything contain has an association to a diagram object. Then, say the diagram object contains a diagram can contain multiple diagram objects. So this is the way of joining up. So we can have a diagram that's perhaps called network overview. It inherits from identified object, so it will have a name and it will have an ID. And we can say whether the orientation is positive or negative. That gets into the right-hand rule. And what it really defines is, does your Y go up from the bottom left or go down from the top left? And also part of that's also whether the Z goes in or out, but quite often that's not really used because most diagrams are just two-dimensional. So identified object could have multiple diagram objects because it may appear within multiple diagrams. And within our diagram, we can set what the initial view, the top left and bottom, are two corners essentially of an initial view. So that you may have a large overview diagram, but you want the person's initial view of it to be one small part of it, or the whole thing, and we have support for defining that. We can also do things like visibility layers. So within a diagram, you could have multiple visibility layers, so you can make sure that you're placing things in the layer you want, or you can turn layers off and on depending on how your software chooses to support it. And then we could have a text diagram object. So this inherits from diagram object. It may not have an association with an identified object. We may just want to place labels on the diagram. And so we can put a text diagram object and put a string in there to represent what is actually labeled on the system. And then finally, we have our diagram object style. This allows us to, against a diagram object, we can predefine a number of different styles. And this is not us defining graphics. The way we have been using this is more we're agreeing upon a set of kind of string values that says what the style is on this diagram object, and it can be used as a hint for how it's rendered upon the receiving system. So I'll go into the diagram object style a wee bit more kind of later on. So I'll give an example of how this can actually look when we get into rendering it. So if we consider a diagram layout example, we will have a few different components here. It's a slightly different diagram to what I had before, just to keep it a wee bit simpler. So in this example, we've got our busbar section, we've got a breaker, power transformer, synchronous machine, another breaker, and a AC line segment. So if we're going to think about these and how we want to do them as a diagram, well, it's obvious that a number of the components there we can do as a single point. We'll just give the center point for them on the diagram. So if we've got our breaker, power transformer, synchronous machine, and other breaker, we can model them there as a single point, so a diagram object point. If we've got our bus bar at the top, we want to define it as 3 points. We could perhaps get away with it as 2, or we might decide we want a point in the middle where it's joining. The AC line segment down there also has 3 points against it, which represent our start or bend point, what might be the end of the line. The diagram objects for each of them will then encompass, for some of them it's a single point. For the bus bar section, the AC line segment, the diagram object contains the 3 diagram object points. So if we look at our breaker that we have here, how does that correspond into, this is CIM XML. So this is CIM RDF XML, which is a way of representing the CIM data it's a W3C standard XML format. So here we have our breaker, which is a diagram object, and a diagram object point, which is an XY position. There's references between them. So that's how we represent the breaker and its diagram object. For something like the bus bar section, it's going to have multiple points. So the resulting serialized data is slightly bigger. We have our bus bar section, we've got a diagram object, and then we've got 3 points with 3 different XY positions and sequence numbers on them. So we can see what the drawing order would be there. From left to right, you can see the Y positions are the same, and they all refer back to the same diagram object, and the diagram object refers back to the bus bar section. So if you consider how you actually want to draw and render these, so the bus bar sections in the AC line segment, obviously we're going to draw them. We've got our sequence numbers, so we can draw them in like this. But obviously what's missing from this as well, we've got connections between them. But if you remember back to the model we looked at before, we have terminals on the pieces of equipment, and we can assign diagram objects to the terminals to give us the routing between those parts. So here we have our breakers, power transformers, synchronous machines, AC line segment. The terminals each have a diagram object with multiple points against them. And that allows us to define what are the lines between the points of the network. So here it means we can have a wee bit more flexibility in how we do the routing between the different components, but we're still tying it back to the CIM objects. We're still tying it back to something within our domain model. So here the breaker, for example, has a terminal, and the terminal then has a diagram object with a couple of diagram object points on them that represent the lines that are drawn there for the terminals between the components. So if we look at this is what we have in our CIM representation. When we pull it into a receiving system, then it knows it's a synchronous machine, so it knows the icon it needs to use, it knows the breaker and power transformer icons, and it knows AC line segment, how it would render one of those with the rendering. So we can end up back with the diagram that we had. The colouring could come from voltages, the colouring could come from phase, the colouring can come from containment, but once again, that can all be derived from the domain model. We're not requiring the display layout to include information of what colour you want to use, because our experience is that actually is something that's defined by looking at the characteristics of the data and using your own internal logic to decide how you want to colour it and how you want people to be able to change the colouring. But we still maybe want to be able to define graphical styles to let people have some hints about perhaps changing the icons or changing things depending upon the data and what we're using. So we're not seeking to define how graphics are rendered, just the layout, but we want to give these hints and style references, and they can be used to interpret the incoming data. So it makes, but a lot of the time we find that we don't necessarily need them because we can derive some things like known states and known types from the domain data. But there is examples where this could be required. So styles are useful if you have multiple diagram objects for one domain object, for example. So if we have a single power transformer, we may actually have 4 diagram objects here on the screen. So if you have 4 diagram objects tied to one domain model, how do you know which is for which? So we want to have appropriate style IDs against each so that senders and receivers can coordinate what's to be shown. So in the simple example I have there, some of the style IDs could be the primary winding that's coloured. So we want to tell people that the first diagram object is for the primary winding and where it goes. The second one could be for the secondary winding, so that we know that the diagram object's placement there represents a secondary winding, which may give somebody a hint that they're going to need a slightly different way of representing it because it's secondary. We may have a transformer local name, so we're going to have a diagram object, we're going to see where it goes on the screen, and we're going to tell them that style ID, and internal logic can tell us that, well, what we do is we pull the name of the domain object and put that at that point on the system. And then we can have another one here that's a transformer tap changer type. So we know we want an icon so the person can instantly see what the tap changer is against it. Our internal logic would go and look at the power transformer, it would look at the references, it would find out which tap changers it has and pick the appropriate icon. But we know that the point in the screen where it goes, the diagram object is going to go at that location. So I think that's a kind of quick summary of how we do the CIM diagram layout. And as I say, the key thing is it's not about exchanging graphics, it's about exchanging layout. And systems can use their own icons, styles and colours, but the layout and placement of the components is the same. So it means it can be easily integrated with the network data. We can use existing interfaces, we can use existing serialization formats, existing databases, RDF stores, whatever it is that you're using for storing your CIM model. And the standard's flexible, it can be used for different types of diagrams, whether it's single line, geo-visual, dynamic block modeling. And we did actually use this standard for ENSO-E, and we successfully exchanged schematic diagrams for multiple networks between the vendors at the ENSO-E interrupt tests for the last 2 or 3 years in Brussels. So a number of the large vendors do support this, and the general feedback we got from them was it was relatively simple for them to support and met in with their own internal kind of like data structures, and it has worked well. Where it was useful was to start getting into things like, what is the standard rotation for an icon? If you specify it as being 180 degrees, what are you assuming it looks like at 0 degrees? And we started into what are the coordinates going to be in? We personally just generally work in pixels. Other people work in millimeters for print. So do we have to? So we're looking at how do we, for the next version of the standard, how do we look at extending it to include things like letting people know programmatically and from the data what's the type of coordinate system being used and so forth. So the things that have come out of it is not so much things that were wrong, it's things that would be nice to have to make it easier to deal with. Or how can we start hooking diagrams into pieces of equipment so that we know this is the diagram for a substation, and so forth. So I think that's me done for that bit. So
great. Whoa. All right, so here's what I would propose, and some very kind person said, gee, why don't we set up a wiki to submit questions and provide answers via, and I think that's a great idea. We will go to work on something along those lines. So what I will attempt to do is take the pictures that are, goodness, the questions that have come in so far and sort of synopsize them, and we'll get our panel to answer them, and the folks from CIM user group will help us figure out how to make them available to all of you. There have been, in addition to technical questions, a number of questions that have come in about how to get to the content of this webcast after it's over. And so I just wanted to point out again that if you go to the technical webinars quick launch bar on the left side of the CIM user group website, it will take you to a page that will show the UCAI YouTube channel list of presentations, and our 3 webcasts from this series will be shown in there. There was also a question about being able to get access to the presentations today, and what I would tell you about that is if you go to previous meetings and you look at the Oslo meeting website, there is a CIM University link, and you will find our agenda there for CIM University, and the presentations that are shown there are very similar to what you saw today, and they are available for download right now. So with that, I would like to just thank you for your attendance and your patience with us as we ran over. It is incredibly heartening to see this much interest in the use of the CIM for network analysis purposes. Thank you guys, and we'll see you again next Tuesday.